All right, as we start our discussion on electrochemistry, we're going to be focusing on redox reactions. So today what we want to do is we want to review redox reactions and balance these redox reactions in both acidic and in basic solutions. So just to recall what oxidation and reduction actually is, oxidation refers to the loss of electrons. So that means that the species is becoming more positive, and reduction looks at the gain of electrons, which means the species is becoming more negative. So just because a species is gaining or losing electrons doesn't mean there will be a sign change in the oxidation number. So for instance, let's say that we had vanadium 3 plus going on to form vanadium 2 plus. So as we look at this, we can see that vanadium is becoming more negative, but the sign is not changing. So if we wanted to finish out balancing this half reaction, we would have to add a single electron on this side. So now let's go ahead and check out a few other half reactions. So I have two for you here. We have zinc going on to form zinc 2 plus, and then it's balanced with 2 electrons. And then we also have copper 2 plus 2 electrons yielding copper. So let's go ahead and look at the oxidation number of zinc and copper. So zinc in the reactants has an oxidation number of 0. And then in the products, it has an oxidation number of plus 2. So because zinc is becoming more positive, it's losing electrons, this represents a species that is being oxidized. Whereas with copper, you have copper 2 plus, and it goes on to gain 2 electrons and form copper with an oxidation number of 0. So here, it's gaining electrons, so this represents that copper was reduced. So another way that you may see this is in terms of the oxidizing agent or reducing agent. So the oxidizing agent refers to what's actually being reduced, and the reducing agent refers to what is being oxidized. So now that we've done our quick review on redox reactions, let's go ahead and learn how to balance redox reactions in acidic and basic solutions. So the general strategy for writing a reaction in an acidic solution is you want to start out by writing the unbalanced half reactions. So for instance, as we look at this particular example, we have manganese 7 oxide plus iron 2 plus going on to form manganese 2 plus and iron 3 plus. So what we would do is let's consider iron in this case. So iron is undergoing oxidation because we have Fe2 plus going on to form Fe3 plus. So it lost an electron. So to balance this out, we would have to add an electron. So we're done with this reaction. Let's go ahead and look at the manganese. So here we have, for reduction, we have MnO4 minus. Guess I forgot my phases up here. There we go. It's not just a phase, Mom. So we have manganese O4 minus going on to form manganese 2 plus. So as we look at this, we can tell that this reaction is nowhere close to being balanced because we don't even have the same species on both sides. So the first thing that we'll do is we will have to add hydrogen ions and water to balance the atoms. So we'll add water to balance the O's. So we have 4 oxygens in the reactants, but we don't have any oxygens in the product, so we need to add 4 H2Os in the products. So now the oxygens are balanced, but the hydrogens are not, so we need to balance the hydrogens, so we will add hydrogen ions to the reactant side, so that's 8 of them, so we have 8H plus. All right, so now that we have the hydrogens and the oxygens balanced, we need to make sure that we balance the charges. So we can do this by adding electrons. We already did this in the first example by adding the electron in the products, but down here what we can do is we can look to see what the total charge in the reactants is versus the total charge in the products. So for instance, if we look down here, we can see that on the left-hand side of the reaction, we have 8 plus from the hydrogen, and then a 1 minus from the MnO4 minus. So that means that overall on the left-hand side, we have a total of plus 7. That's the charge. So we have 7 plus charge. And then on the right-hand side, we have a total charge of 2 plus. So to balance this out, we're going to have to add 5 electrons to the left-hand side. So now that we have the charges balanced, we're going to have to combine these reactions. So the way that we do this is we look at the number of electrons in both the oxidation and the reduction process. So we have 5 electrons in the reduction process, 1 electron in the oxidation process, and we need to get these to cancel out. So we're going to balance charges by multiplying through by the least common multiple of the electrons. So here we'll have to go through and multiply this top reaction by 5. And then the bottom reaction we just have to multiply through by 1, so it's good. So as we go through and look at the top reaction, this becomes 5 Fe2 plus yields 5 Fe3 plus 5 electrons. So now we're ready to combine these two equations and to cancel anything out that occurs in both the reactants and the products. So as we look at this reaction and this reaction, you'll notice that the 5 electrons cancel out. We have 5 electrons in the reactants here and 5 electrons in the products up here with the iron. So now we need to look. So sometimes what we'll end up seeing is we might have H pluses that cancel out or H2Os. But here, since we didn't have to add water or the hydrogen ion to the first reaction, they won't cancel out. So what we can do is we can combine these, and we'll get an overall net reaction. That is 5 Fe2 plus 8 H plus MnO4 minus yields 5 Fe3 plus. So again, we're just combining these two reactions. Plus Mn2 plus 4 H2O. So now we've balanced this redox reaction in an acidic solution.